Now we'll cover the matrix inverse. Only square matrices can have an inverse, and even not all of those will have an inverse. But here's how it goes. Let's say we had a square matrix A. There was some matrix B such that if I either pre or post multiply A by B, I would get the identity matrix. And that B is called the inverse of A. We use this special notation for it. A with the superscript -1, meaning the inverse of A. So here I can pre-multiply A by its inverse or post-multiply A by its inverse, and I get the identity matrix. If its inverse exists. How do we know if it exists or not? If A's determinant is not 0, then it has an inverse. If A's determinant is 0, then we say A is singular and doesn't have an inverse. If you'll notice, when we covered basic matrix operations, we had plus, we had addition, subtraction, and multiplication. We didn't have division. But at least when it comes to 3 by 3s, we can multiply by an inverse instead of dividing. If the determinant is 0, it's kind of like dividing by 0. So if the determinant is 0, no inverse. It's a singular matrix. Determinant is not 0, it's a non-singular matrix, and it has an inverse. Here's some properties. The inverse of an inverse is the original matrix. If I want the inverse of a product, I reverse the order of multiplication and take the individual inverse. AB inverse, inverse times A inverse. Inverse of a transpose is the transpose of the inverse. You can just write these down. I didn't make a big deal out of these properties when I taught it. One use of it is solving systems of equations, assuming the determinant exists. So we already have a square matrix, so it has n equations in n unknowns, so it's square. And if the determinant is not 0, it's the case of having exactly one solution. If the determinant is 0, we don't know if it's an inconsistent matrix or has infinite solutions. You can't really use the inverse. But here's a little example of some matrix arithmetic or algebra. Here is our original system of equations, AX equals B. If I multiply both sides by A's inverse, when it exists, I have A inverse AX on the left, A inverse B on the right. A inverse A is just the identity matrix, so it's just X on the left. So if you can invert this matrix A, just this simple matrix multiplication to get the solution. But inverting a matrix is probably no easier than doing the Gaussian elimination we taught originally. But if you already have the inverse hanging there, then it's easier than going through the Gaussian elimination. How to compute this guy? We have to talk about adjoints. And here's how to compute an adjoint. First, we have this matrix, this generic, say 3 by 3, and that's the worst you'll probably ever have to do by hand. Each element in this matrix, or each location in the original matrix, has a cofactor. Remember, I told you how to compute cofactors earlier. But the C11 cofactor is based off the matrix left after you get rid of row 1 and column. So this 3 by 3 is going to have 9 cofactors. And remember the signs. If they're not just minor determinants, you have to alternate the signs as you go around. Here's some examples of these cofactors. 1-1 term is 1-1 minor determinant. 1-2 term is going to be the 1-2 minor determinant with a negative sign, etc. So you could compute those 9 cofactors. Adjoint is then the transpose of this matrix of cofactors. Kind of get things out of order. This is when we get to a 3x3. If A is just 1-1, 1x1, adjoint is just defined to be 1, or the 1x1 identity matrix. Single element matrix, it's just 1, and 1 is the element. 2x2, and here's what we want. Here's a trick. You switch the main diagonals and change the signs of the off diagonals. See, if this is your original matrix, A22 goes up here and A11 goes down there. You just change the signs of the off diagonal guys. 2x2 is easy if you can remember this sort of X operation. Switch the main diagonals, change the signs of the off diagonals. Here it is for the 3x3 matrix. Yeah, I'm now realizing I did that in reverse order. Should have done 1x1, then a 2x2, and then when it gets to 3x3s, you have to do all this computation. So how do you calculate an inverse? It's the adjoint matrix divided by the determinant. This will only apply when the determinant is not 0. Otherwise, it's like dividing by 0. A would be singular, it would not have an inverse. 1x1, like in this case, the determinant, remember, was -3. By definition, the adjoint was 1, so it's just the reciprocal of the element. For 2x2, let's do this guy as an example. Well, the determinant is 4 minus 6 or -2. What is the adjoint? Flip these guys, so I have a 4 up here and a 1 down here, and change the signs of these guys. So it's -3, -2. And I divide by the determinant. I by -2. The inverse. To satisfy yourself, if I multiply this guy times that guy, either in front or behind, you end up with the identity matrix. For 3x3, it's a little tedious. You have to find the whole determinant. Then you have to find all 9 cofactors. I'm not going to go through all this. Let's see. I think I expanded this by the bottom row because there's a 0 there and a 1 there. So 1 guys will be -1, 2, -0. So just be 2. Then I have plus, minus, plus, -4 times its guy is 4 minus 15. So its determinant is 78. It's not 0, so it's non-singular. So yes, it does have an inverse. You have to compute the adjoint. You have to go through each one of it. 1-1 term, this matrix will be 0 minus 2, 4, 0. By the way, don't multiply by the 2 here. You're just strictly doing the cofactors or minor determinants. You're not expanding by. So don't multiply by this 2. That's one of the common mistakes that my students made. So we have 9 little cofactors to find, 2x2 matrices. I'm not going to go through that. You'll have this, first you'll have this matrix of 8 minus 2, 12, corresponding to these guys. will be this. Then you need to transpose that. Here is your adjoint matrix. The inverse is then this matrix divided by the determinant. So here is your inverse. And this right here is a good enough answer. You can carry out the fractional arithmetic, simplify things down to this. I didn't require my students to do that. This was a perfectly good answer right over here. So yeah, calculating an inverse can get a little bit, they're pretty important things. And next we're going to get on to eigenvalues and eigenvectors. That'll be fun.